Alright, let's continue. Let me open the table of content first. Okay. We are still in this chapter 20, patching smaller tables, and still in section 20.3, multi-level page table. Let me open that. Where is it? Okay. Am I lagging? I hope not. Okay. Alright. We are still in section multi-level page table here, trying to understand what is it called? Division, I guess, of the multi-level page table. Like, how do we get the page directory and this page of page table? Okay, previously, I think in this one, I'm kind of confused, right, about what is the page of the page table, right? And well, I assume it is the page from big page table or linear page table here. Okay, and inside this page table, right, we have a bunch of pages. The page of page table, okay. The page of page table in this case is one of the pages from those big tables. I assume something like that. So this is called page of page table, or wait a minute, is that correct? Maybe not on this one. Page of page table, page 1 of page table, not allocated. Oh, okay. Maybe this. Okay, maybe this one mean this one. You know, the invalid. What is it called? The invalid in the page directory here. Page 1 of page table not allocated, and page 2 of page table not allocated. This one, the page 2. The one that is allocated is page 0 and page, I guess 3. This one with page frame number 201. This page 0 is allocated. This page 0 of page table is allocated, and this one, the last page of, or the page 3 of page table, is also allocated. Okay, right. Yeah, I think that's what it means. Not necessarily this is related to this one, right? Previously I thought that this one, page 1 of page table, is related to this one, but after my analysis it looks like this is related to this page directory instead. Maybe something like that. Okay. Yeah, so the page table in this case means this one. What is it? The index, I guess. In this case, we represented by page frame number, but if it is virtual memory or virtual address, we represented by virtual page number, something like that. So yeah, if I understand correctly, the page table in this case means that the page inside of the big page table or the linear page table, if I understand correctly. Okay. Yeah, we are trying to understand this with the example, right? The example here is the address space size 16K with 64-byte page size. So its page we have 64-byte size, maybe something like that. So we have, what is it called? We have some kind of range, maybe something like that. For example, something like this. This is what is it called? This is one page, right? Let's say if we have the address space size 16K with the page size 1K, we will have 16 pages, and inside those pages we have what is it called? We have some kind of range in there from 0 to 1023. If it is the, what is it? If the page size is 1K, right? So if this is 64 byte, so maybe for one page we have 0 until 63, something like that. And then we have 64 until, what is it? 127, maybe something like that. Yeah, this is the n negative 1, the n minus 1, because we start from 0, right? Okay. And so on until 256 or 255, I mean. Maybe something like this. So yeah, these entries mean the page 256 page, and inside those pages we have 64 entry, page table entry, maybe something like that. Again, I'm trying to understand how this works. I mean the term is interchangeable, I guess. For example, it is called entries here, and later on there's another entry, right? So is that the same entry or different entry? That what make me confused, I guess. Okay, even if only small portion of the address space is in use, right? So we have page 0 until page 255. In this scenario, address space size 16K with 64 byte page size. Okay, each page have 64 byte size, something like that. This example, virtual page 0 and 1 are for codes, right? Again, it is called page now, not entries. So there is that. Virtual page 0 and 1 are for code, virtual page 4 and 5 for the heap, and virtual page 254 and 255 for the stack. The rest of the pages of the address space are unused. This example, figure 20.4, 16K address space with 64 byte page size, I mean. Okay, so it's this one consists 64 byte, I guess, something like that. Okay, the rest of page are unused. To build two-level page table for this address space, we start with our full linear page table and break it up into page size unit. Okay, now that we understand that this is the page, right? All of this, what is it called? All of this part is page. So the page size unit is basically, if I understand correctly, we are what is it called? We are treating this page as its own page table, something like that. Okay, recall our full table in this example has 256 pages, assuming its page table entry is 4 byte in size. So I assume this page table entry size is the size of the information contained in this bit, maybe something like that. So again, what is it called? We need to store the bit information for of this entry, right? And then reference those those entry information to access the real information. If I understand correctly, it is something like that. Okay, those are page table 1K, right? The total page multiplied by page table entry. So we have 1k page table size, right? This is only the size of the page table, not the information that this page store, if I understand correctly. So this is the size of the page table, 1k, right? Given that we have 64 byte page, the 1k page table can be divided into 16 pages. Okay, divide into 16 pages. Let me recheck again. 1k divided by 64. Yeah, we have 16 pages. Assuming we have this one. Okay. And then each page can hold 16 entry, you know. So imagine something like this. I guess, let's say this is page 0, and then this one, I guess something like this, maybe. Yeah, similar to figure 20.3, right? This is the page 0, and inside this page 0 we have this, what is it called? This entry, I guess. So inside this page we have this 4 entry, and we only have, in this case, 4 pages, I assume. And each page have 4 entry. Okay. And in this case, each of these 16 pages have 16 entry. I mean, let me check. Only 256. So here, what is it called? The total page round up to 256 again. Alright. What we need to understand now is how to take a virtual page number and use it to index first into the page directory and then into the page of the page table. Right. Again, the page of the page table in this case is the page from this what is it, linear page, I guess, this one. So when we think about this page of page table, think of it like the big page table, the page inside this big page table before we are chopping that up, maybe something like that. Okay, index first into page directory and then into the page of page table here, something like that, and then going into one of these pages from the linear page table or the big page table. Okay, remember that it's yeah, I think this is its page directory. Okay, remember that each page directory is an array of entries, thus all we need to figure out is how to construct the index for each page directory from pieces of the virtual page number. Okay. Let's first index into the page directory. Our page table in this example is small, 256 pages, spreads across spread across 16 page table, I guess. 16 small page table, maybe something like that. So 256 pages here is spread across 16 small pages. And inside of this small page, we have 16 entries. Maybe something like that. Okay, 256 pages spread across 16 small page table with and each small page table have 16 entries, or PTA, I guess. Page table entry, maybe something like this. I mean, we are what is it called? We are break up the linear page table into page size unit, right? So I assume this page will become its own page table, you know. I mean, like the chapter title here, smaller tables, right? We have what is it called? Instead of one big page table, we have multiple small page table, something like that. Okay. Our page table in this example. Okay, the page directory needs one entry per page. Okay, the page directory needs one entry per page of the page table. So I assume this is what is it called? For this page directory, right? For one page directory, it needs one of these small page table, I guess. And that's why we have 16 entries here. 16 page directory entry. Again, it is similar to this one, right? Each page table entry have one page from this big page table. That's why when we have 16 small page table, I guess we have 16 page table entry. Maybe. Okay. Yeah, this figure 20.3 really helped me understand how this works, I guess. Okay, that's why we have 16 page directory entry. As a result, we need 4 bits of the virtual page number to index into the directory. I'm assuming that 4 bits here is from the exponent of 16 to power 4, guess. It becomes 16, right? So that's why we need 4 bits of the virtual page number to index into the directory. In this case, we use the top 4 bits of the virtual page number as follow. This one, page directory index. Okay. When we extract the page directory index, or pt index for short, from the virtual page number, we can use it to find the address of the page directory entry. Can use it to find the page, to find the address of the page directory entry with a simple calculation. Page directory address equal page directory base plus page directory index multiplied by the size of page directory entry. Okay. Alright. Wait a minute. Like this one. To find the address of the page directory entry. Okay. This is the base address, and I assume this is maybe some kind of offset. Maybe. And then we found the page directory entry, and I assume page directory entry in this case mean this one, right? So after we find the address of this page directory entry, we can access the data inside of this address, this one, right? Okay. This result in our page directory, which we now examine to make further progress in our translation. If the page directory entry is marked invalid, we know that the access is invalid and thus raise an exception. If, however, the page directory entry is valid, we have more work to do, right? So let's assume we already have the address for this page directory entry, right? if it is invalid like this one, like the page 1 here, like the page directory entry 1, I guess, if it is invalid, then throw an exception, right? If it is not, then we have more work to do. Something like that. Okay. If the page directory entry is marked invalid, right? We raise an exception. If the page directory entry is valid, we have more work to do. Specifically, we now have to fetch the page table entry from the page of the page table point to by this page directory entry. Yeah, this phrasing, I guess that's what it is called. This phrasing can be confusing, I guess. From the page of the page table point to by this page directory entry, we have to fetch the page table entry from the page of the page table point to by this page directory entry. So I assume pointed to. So this page directory entry, if I understand correctly, this page directory entry points to the page of the page table, and then we fetch this page of the page table. So if we take a look at this figure 20.3, I assume we are fetching this page. I'm not sure if we only what is it called? We only fetch one of the entry from this page, right? Page of the page table, or we are fetching the entire or we are fetching the entire page entry here. Maybe we fetch the entire page entry. Yeah, but I'm still not sure. Especially we now have to fetch the page table entry from the page of the page table point to by this page table entry. Let me take note here. If the page directory entry or PTA is valid, one of the things to do is to fetch the entries or PTA page table entries from the page of page table that PTA points to. Yeah, maybe something like this. One of the things to do is to fetch the entries from the page of the page table that the page directory entry points to. Okay. Still not sure if it is all the entries or only partial. Yeah, that is something to consider, I guess. Still not sure if we fetch all entries or partial entries from the page of page table. So I put this in maybe something like this. Okay. Alright, to find this page table entry, we have to index into the portion of the page table using the remaining bits of the virtual page number, like this. The page table index. Oh, okay. So after we find this this page directory entry, right, we need to find the index, I guess. The index of this page entry, page table entry, the small page table entry. Okay, so maybe we are not fetching all of this entry, only partial. Maybe. Okay. Alright, where is it? Page table index. Yeah, let's call this small page table index to differentiate between this linear, right, this linear page table and this where is it, this small page table. Again, if we use the same term, that can be confusing, at least for me. What page table are we talking about here? Yeah, something like that. Okay, so does that mean, yeah, this is what is it, page directory entry, right? And then this one is the page table index, I guess. Yeah, this range for the page table index, and then each of that index have an offset. What do I? Yeah, the offset is maybe 0 until 64. Offset. Okay, let's call this base directory index. No. Yeah, maybe something like this. This is the base directory index, and this is the page table index, and this is the offset. So let's say we have page directory index 0, and then we have the page table index 1, and then the offset is, let's say 2, right? And we will use this figure 23 as an example. So this is the page directory index 1, index 0 I mean, index 0, and this is the page table index 1, and there is the offset 2. So if we use this as an example, I think it would be something like this: 201 plus 13, right? Then figure 3, 13, and then plus maybe 2, the offset 2. This is page directory index, and this one page table index. This is the offset. I assume something like this. The division, I guess. Yeah, page directory index, page table index, and then the offset. I think that is in the figure, this figure, right? So instead of having one virtual page number as the index, we split that into 2 index: the page directory index and the page table index, and then the offset. Okay. This page table index, PT index for short, can then be used to index into the page table itself, giving us the address of our page table entry, right? So we got the address of the page table entry. To access the information inside those address. Okay, we do this, the left shift. Okay, and then add that with the index to get the entry address. In this case, in the figure 20.3 case, yeah, maybe something like this: 201 and then 13 to access the entry address, and then we add the offset to access the data. Maybe, yeah. Let me reread this again. Okay, write something like this to get the, what is it called? I guess the base address for this page directory index. and then with that base address we add the page table index. Okay, note that the page frame number obtained from the page directory entry must be left shift into place before combining it with the page table index to form the address of the page table entry. Okay. Yeah, I'm assuming this is not the offset yet, right? We haven't get the offset yet, so maybe this is the base address for this page table entry. Yeah, let me show the figure 20.3. What I mean by the base address is the base address of the page table entry is something like this. The entry 0, and then we add the offset from there, from the entry 0, if I understand correctly. Okay, to see if this makes sense, we will now fill in a multi-level page table with some actual values and translate a single virtual address. Okay, let's begin with the page directory. For this example, left side of figure 20.5. We'll now fill in a multi-level page table with some actual values. And translate a single virtual address. Okay. Let's begin with the page directory for this example. The left side of figure 20.5. In the figure, you can see that each page directory entry or PDA describes something about a page of the page table for the address space. Okay, right, I think this one. In this example, we have two valid regions, two valid page, I guess, in the address space at the beginning and end. Yeah, this one and this one, right? And a number of invalid mappings in between. Okay. In physical page 100, the physical frame number of the 0 page, right? Of the 0 page of page table, we have the first page of 16 page table entry. We have the first page of the 16 page table entries for the first 16 virtual page number in the address space. We have the first page. In physical page 100, we have the first page of 16 page table entry for the first 16 virtual page number in the address space. See figure 20.5 middle part for the content of this portion of the page table. Okay, page of page table here. And inside of this page, we have, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 6. Okay, for this page we have 16 entry, I guess. 16 page table entry, right? Yeah, I'm still not sure about this one. We have the first page of the 16 page table entry. Oh, and this one is also 16. Is that it? The first page of 16 page table entry for the first 16 virtual page number in the address space. Oh, maybe this one. Again, in physical page 100, we have the first page of the 16 page table entry. I'm assuming the page table entry is this one, right? If we have the first page from the 16 page table entry, or the first entry, I guess, then maybe this one is what this statement talking about. For the first, oh wait, oh no, I don't think that's right. Okay, maybe this is just an explanation about this one. Inside the first page, or page 0, I guess, we have 16 page table entry. This one, yeah, this is 16, right? The middle part here. We have the first page of 16 page table entry for the first 16 virtual page number. So the first 16 virtual page number is in the first page, or in this page 0. Maybe something like that. Let me fetch the entry. Okay. Yeah, we only fetch one entry, if I understand correctly. And then the page 0 of 16 page table entry for the first 16 virtual page number in the address space. Okay. Means that we have the first 15 virtual. The linear is table in the page 0, maybe something like that. if we take a look at this one, right, by combining the page directory index and page table index, we have the virtual page number, which is the index for this linear page table arrangement. Okay, and then this page of page table contains the mapping for the first 16 virtual page number. In our example, virtual page number 0 and 1 are valid. The code segment, oh, this one, virtual page number 0 and 1, right, as are 4 and 5 the heap. Okay, this is 0, this is 1, index 1, this is index 2, index 3, index 4, and index 5, right, 4 and 5 for the heap. Okay, thus the table has mapping information for each of those pages. The table has mapping information for each of those pages. The rest of the entries are marked invalid. The other valid page of the page table is found inside page frame number 101. This one. Okay. This page contains mapping for the last 16 virtual page number of the address space. See figure 20.5 right for the tiles. Yeah, this one. I see. So maybe we can think of the big page table or the linear page table as the address space itself. I'm not sure. Okay. In the example, let me take a look at chapter 18, I guess. Is there any figure or illustration? Yeah, this is the page table entry information. Okay. Maybe not. Okay. Page frame. Okay. Yeah. In the example virtual page number. Okay. In the example, virtual page number 254 and 255, the stack have valid mappings. Hopefully what we can see from this example is how much space saving are possible with a multi-level index structure. In this example, instead of allocating the full 16 pages for a linear page table, we allocate only 3. One for the page directory and 2 for the chunk of the page table that have valid mappings. Okay. Yeah, maybe I'm not sure if we can think of the address space as the linear page table itself. Okay. And so for now, maybe let's think of this like the linear page table, something like that. We allocate only 3. One for the page directory and 2 for the chunk of the page table that have valid mapping. Okay, we allocate for this page directory and then for this one the page of the page table, the page from the big page table, something like that. Or maybe we can call this page of the address space. I'm not sure. Okay. Where is it? One for page directory, 2 for the chunk of the page table that have valid mappings. The saving for large 32-bit or 64-bit address space could obviously be much greater. Alright. Finally, let's use this information in order to perform a translation. Here is an address that refers to the 0 byte of the virtual page number 254. Okay, this one, this hex number, I guess 3FXT, or this binary digit. Recall that we will use the top 4 bits of the virtual page number to index into the page directory. Thus this one will be choose. I think this one will choose the last 15 if you start at the 0 and 3. Okay, 0, okay, and 3 of the page directory above. We choose the 15 entry of page directory above. I guess this one, right? Oh, and this is the stack. Okay. Where is it? This point us to a valid page of the page table located at address 101, right? This one. Okay. We then use the next 4 bits of the virtual page number. I assume it is this one Oh no, wait. Oh, this one. Alright. The next 4 bits, right? To index into that page of the page table and find the desired page table entry. And this page is the next to last. The 14th entry on the page and tell us that page 254 of our virtual address space is mapped at physical page 55 by concatenating page frame number equal 55 with offset offset 0. We can transform our desired physical address and issue the request to the memory system. Okay, physical address, page table entry, I've saved the base of page table entry and then plus offset. Okay. The index into that entry of the page. Yeah, I'm not sure if. Okay, maybe in this case it is called page of the page table. This point us to a valid page of the page table, right? Point us to this 101 page address, and then inside those pages we index into the entry, the entry inside those page table entry, something like that. Okay, index to the entry and then to get the and then to get the actual data, right? We add the offset. Okay, let me check. Page directory index, right? And then page table index, and then the offset. Okay. Split across 16 small page table. Okay. I'm trying to understand this. Okay, this is the page address. Right, this is the page address, and then we index into the entry address, I guess. Okay, the 14th entry on the page. This one, the 14th entry of the page. Maybe something like this. Get the page address. Get the page table entry address, I guess. Page table entry address, and then get the actual address. Maybe something like this, the step. First we need to get the page address, and then we get the page table entry address. Again, if we combine this with this, right, we got the virtual page number. It is from chapter 18 here. Yeah, something like this maybe. This is the index in the linear page table, right? After we get the index, we get the offset. The transitive virtual address that the process generates. Okay. Alright. And then to get the actual address, we had the offset here. Okay. Yeah, by concatenating page frame number 55 with offset 0, we can transform our desired physical address and issue the request to the memory system. Right, something like this. Oh, okay. You should now have some idea of how to construct a two-level page table using a page directory which point to page of the linear page table, maybe something like that. Unfortunately, however, our work is not done. As we'll now discuss, sometimes two-level of page table is not enough. As I will now discuss, sometimes two-level of page table is not enough. Okay, this two-level of page table is already confusing, but it is not enough. More than two-level. Okay. Oh, hello, Swartz. These pieces are not easy. Well, I think that is subjective, but for me, yeah, it might not be that easy, but doesn't mean I will just give up, you know. I will take that as a challenge, trying to understand this. Okay, Hello, Kinsley. Welcome, welcome. Yeah, currently we are on chapter 20. Smaller page table. Basically trying to, what is it called? To solve a problem that, what is it called? To solve the problem that the page table is too big, you know. And one of the solution is to have a multi-level page table, something like that. So yeah, we are trying to reduce the page table to reduce the memory usage, maybe something like that. And then, well, I think let's continue this on the next session. More than 2 level page table. Yeah, I'm trying to digest what I learned. Okay, so that's it for now. Thank you for watching and see you next time. Bye bye.